Hi everyone, I'm Roman Meyer and I'm currently the thing standing between you and lunch, and I'm very aware of that. That also means I get to decide when you have lunch, so I'm just saying. Hi, I'm here to talk to you about SEL4 as a CPU driver, and we'll figure out what that means together. We'll talk about some more things as well. But this is work that is done at the systems group in Zurich, where we're doing work with my supervisor, Timothy Rusko and Mothi. And primarily this is done with Ben Fiedler, who's not here, and Zikai Liu, who's here. And so this is all there we go. This is all, right. So the way that I like to start this presentation is by giving everything away at the start. So if you don't remember anything, remember the contents of this slide. The problem that we're trying to solve here is that, first of all, the SEL4 hardware assumptions don't really match the reality of the actual hardware. And second of all, modern SoCs are much more distributed systems of untrustworthy firmware than any other model that you might have in mind. And second of all, our approach for trying to solve this problem is that we first formalize the hardware and derive explicit formal software trust relationships. And then we can run SEL4 as a CPU driver with assumptions derived from the hardware as it actually looks like. And so this is very early research. And if you have any ideas, if you don't like what we're doing, if you like what we're doing, if you have criticisms or suggestions, come talk to us. We'll be here at the summit at least for today, and then we'll be in Sydney until Monday. So you have time to talk to us. So let's dive into the problem, shall we? What we've noticed at the systems group is that modern operating systems like SEL4 mostly view the hardware that they're running on as a CPU, and then you have some core memory, you have some I/O, and the I/O does work for you because you send it commands, and then it comes back and says, oh, I've done the work that you told me about. And all of this is connected by a singular bus that connects all of these components. Now, unfortunately, this is the model of a 51-year-old PDP-11/40. And we've sort of moved on, or the hardware people have moved on. We haven't really noticed. The SEL4 assumptions in particular about DMA, now there's a little more here about maybe verifying IMMU and that kind of thing. But primarily, the assumption is that DMA devices are either not present or do not misbehave by, for example, overwriting the kernel. And now I have bad news about the presence of DMA devices on real hardware. This is an extreme example where, for example, where you have a video processing subsystem on an IMX8, which is a production SoC used in cars and phones. The subsystem here is connected to the main system bus by a custom IOMMU. This is not an ARM SMMU. It has a video decoder here, a video encoder here, and this runs firmware. But at least you sort of expect to have a video encoder and decoder in your video subsystem, and you can sort of estimate what it does. This up here are two ARM M0 cores embedded in your video subsystem. They run firmware by the main operating system loading binary blobs into memory, setting the registers of these M0s to that memory, and then telling them to run. They are connected to, So you can already sort of maybe see that this might be a potential security risk. You can run arbitrary cores on these cores, and you might not notice if you're not actively using the video subsystem. And the entity that can write to the addresses where they're executing from can change what exactly they're executing. And in turn, these cores can access your bus and issue arbitrary bus instructions if you haven't properly isolated them, which you might not be doing. And this is only a very small part of the distributed systems that modern SoCs have become. So this is the whole of the IMX8. The part we just were is the small orange blob. And to give you a quick overview of the rest of the SoC, you have some application cores, 4 A35 cores up here, an M4 over here, plus a GPU, a digital signal processor down here. Someone ported FreeRTOS to it, by the way. There's some additional multimedia components over there, 2 cores, an M4 and an M0 operating as system control, highly privileged and can mess up your system, running like partially open source firmware. And all of this is glued together by a system, by the main system bus, which all of these components are connected to. Now, the traditional operating system's view of SCL4, Linux, and basically everything else, is that you have SCL4, SCL4 is up there, as a sort of sun god, sitting on top of this hierarchy and pretending that most of this is essentially just peripheral. You can talk to it, you give it commands, and it comes back, and it's done with its work. But really, what you're looking at here is a de facto operating system that's actually in charge of your hardware, made up of manufacturer-provided untrustworthy firmware. And SCL4 is sort of just cohabiting with the rest of the system. Now, if you don't believe me yet that this might be an issue, to illustrate the potential security issues caused by this state of affairs, we can look at a simplified attack scenario where, for example, we could take over a Bluetooth DSP over an over-the-air attack, which has been demonstrated a multitude of times. And maybe they share some RAM. Like they're both running complex firmware. They need a place to put their data structures. They're not putting them in main DRAM, because at that point you have to ask SCL4, and that's just too much of a bother. So we've just put a few megabytes of RAM there, and our firmware can use it. And let's just use one, because like we have a Bluetooth DSP and a Wi-Fi DSP. Let's save some money. But of course, when the Bluetooth DSP is taken over, it can just write into the firmware data structures of the Wi-Fi DSP, and at that point, you're essentially done. And these things usually don't have an IMMU configuration that's complex enough to protect them. Now, in this example, there's actually an IMMU. But if you're running Linux on your main CPU, it has probably a vulnerability in your driver. And so you can take over the kernel by tricking it into reconfiguring the IMMU configuration and writing into page tables, and then you're done. If you're running SCL4, your drivers are in user space, which is an interesting state of affairs. If you're a little generous with what I've been told about the IMMU configuration capability for SCL4, assuming that SCL4 configures the IMMU such that no device can write into its kernel memory, then this attack doesn't really work and kernel memory vanishes from this map. But user land is still affected, right? You have a driver, and if I've taken over your Bluetooth DSP, I can mess with your Bluetooth driver however I want. And all that is of course still assuming that there's not some random M0 on your SoC that can just write into your kernel data structures directly, because the hardware people thought that was funny. The main point here is not that this may or may not be the case. The main point here is who knows? And if SCL4 doesn't know, if we don't know, who does? And it's probably the people who are trying to break into your SoC and crash your self-driving car into a wall. And so the SCL4 proofs are very powerful, and one of the really cool things that they do is that they make these kinds of assumptions very explicit, and you can maybe start to think about what the hardware is doing. I actually think SCL4, and the conversations I've had with people, there is more of an awareness of this kind of thing in general than if I were talking to Linux people who were just worrying about their device driver somewhere in kernel space. But modern operating systems, including SCL4, have a blind spot for modern hardware and are not managing it as a whole correctly. And so that leads to really weird assumption mismatches, like we just saw. And so the problem that we have identified is that, one, the SCL4 hardware assumptions don't really match the complex reality of modern SoCs. And these modern SoCs are really distributed systems of untrustworthy firmware rather than anything else. And so now we get to talk about how we might be dealing with this problem. So first, we propose that we formalize the hardware and derive explicit formal software trust relationships. And that relates to SCL4 because we can then run SCL4 at least as a secure CPU driver with actual assumptions about who can access which parts of memory and where we might have to investigate further, and so on and so forth. Zooming out a little bit, all of this is happening under the umbrella of the project that we call Kirsch. The end goal is to replace this congealed mass of software, this de facto operating system of firmware and operating systems, with while still supporting legacy proprietary firmware, because good luck getting rid of most of that, including your Wi-Fi driver, which is probably regulatorily locked down. And adapting kernels like SCL4 to understand the structure of the SoC, but also writing custom kernels, because we are an operating systems group, so we can't really help ourselves sometimes. Ending up with a system that understands and is able to manage the SoC as a whole, based on a formal model of what the hardware actually looks like. And for the rest of this, for this approach talk, we'll focus on how we envision SCL4 fits into this model, and what kind of sort of an introduction into what kind of hardware model we're using, or we think we could use. So the high-level method is that we build an explicit, formal trust relationship graph based on the actual hardware, by looking at the hardware based on documentation, etc., writing down a specification, and at that point we get a graph and we can derive inter-software accesses that are either impossible, in which case we're sort of done. If your Wi-Fi driver, if your Wi-Fi firmware can never access a certain part of DRAM because of the way that your SoC is designed, that's a pretty trivial case. But in the other case, but if you can't show that, then you have a case where you might actually have to investigate and figure out why does the Wi-Fi driver need access to this part of memory, etc. You can start to reason about it. The way that we write down this formal spec is that we write down the hardware addressing and translation structure, so the way that a memory request with an address attached to it gets translated through the SoC, based on manufacturer documentation. Now, this isn't always great. Hardware manufacturers really like not telling you stuff. And so we have to make worst case assumptions such that if we show that something isn't possible, it actually isn't possible. And then maybe sometimes we have to go off and test the actual device, or get NDAs, sign NDAs with hardware manufacturers, that kind of thing. But at least we can, step by step, build up a formal base for what we're doing. As a quick example of the sort of thing we're doing, you can have a resource, for example, on-chip RAM. For those of you who've never heard of it, this is quite common, where you just have a small piece of, specialized RAM, a few megabytes maybe, that sits somewhere on your SoC. In the case of the IMX8, actually connected to the main bus, for basically general purpose use of the SoC. If a certain driver needs to save something at a certain point, you just load it into OCRAM. You might have an interconnect, and that interconnect might show the on-chip RAM at address 5000. And then you have two CPUs. They both have their own separate physical address spaces. And that on-chip RAM shows up, for the purposes of this example, at different addresses in both. And if you write this down, if you write down that the OCRAM shows up at this address in the CPU, and it maps to the interconnect like this, and it ends up at this resource, you essentially end up with a very simple graph in this case, where you can trivially see that the CPUs both can access this on-chip RAM, and they share some memory here. And you might have to think about whether you trust the CPUs with this access or not. Now, for the case where we have completely untrusted firmware, let's just call this non-Kirsch, like everything that we're not including in our design. Kirsch essentially has to, Kirsch, which is trusted, has to configure the system protection unit so that you can't access these resources. Let's say these CPUs that we were talking about were some weird M0 cores, and we really don't want to have them accessing our resources. And once you've done that, you've sort of isolated you would have already isolated most of the problem away. And for cores that you do actually control, where you're not running weird hardware manufacturer firmware, we still need system software to manage them, a CPU driver, so to speak. And having an SoC spanning trust network can provide a really strong formal basis for using SCL4. A, because it already runs in many places, which makes it very convenient, but also because the proofs make it very trustworthy. And so in this model, we have SCL4 running from and managing an explicit region of RAM. And SCL4 is, of course, a trusted component in our system. But crucially, for both kernel and user space. At this point, you can, outside of SCL4, reason about accesses to memory that you allocate to SCL4 to use in general, which it then uses for both kernel and user space. And you enable accesses to this explicitly. So, for example, you have accesses from other Kirsch software, and you might say, that's OK, I control all of this software, and I'm reasonably certain that it won't interfere. And then you have some non-Kirsch components which you have to explicitly trust because either they have to write into certain buffers, or you just can't isolate them at all. And then you explicitly trust them. And what you no longer get, hopefully, are cores that you didn't know about suddenly writing into your main kernel DRAM. So that's an overview of our approach, where we formalize hardware and derive explicit formal software trust relationships for the entire SoC. And then we can run SCL4 as a secure CPU driver with assumptions for its entire RAM derived from actual hardware. Now I will very quickly go into the current status of what we're doing so that we have a basis for discussion. For SCL4 as a CPU driver, we're currently using the ARM-Morello fixed virtual platform as a basis. This is for reasons that I haven't gotten into, for time reasons. And we're running SCL4 on top of it. Then we have MicroKit with a service on top of it, a hypervisor, which then remaps to a Linux virtual machine. And that's sort of our use case for SCL4, where we have a trusted base, but we can also virtualize Linux to, for example, take advantage of the Linux drivers, etc. We have the way that we formalize the hardware is through our own custom hardware description language. The whole project there is called Sockeye 3, which is a custom modular specification, domain-specific language for decoding nets, essentially, which is a model that is very similar to the example that we saw earlier and was developed in the systems group. The current Sockeye toolchain is both interactive and generative, so you can interact with the model that you wrote down, but you can also generate things from it, like currently page tables or simple access matrices, etc. And it has a set solver backend to derive more complicated things, like, for example, these page tables. And it's under active development. The last thing we got is a quite significant usability improvement, where we now have an actual DSL. Previously, we were just writing Rust, essentially, where you can, for example, in this case, this is the VPU D and encoders, where you define the resource, you define where exactly they map to, and then you define that you can use this outside of the model that you just specified. We also have work on Cherry, but I haven't gotten into that. It's essentially just a part of if you're going to isolate your hardware, sort of formally, you might as well push that like hardware-based isolation into software and see what happens. And that's why we are working on Cherry, on a Cherry kernel as well. So for future work, we're always working on formalizing more platforms. And if you'd like to learn how, talk to us. So writing down, we have sort of an almost complete model of the IMX8, and we're working on things like the UltraScale Plus and our platforms. If you have an interesting platform that you think might have a bug or a weird behaviors, let us know, and we can work together on formalizing it. Then we're also working on extending Sockeye 3 with finer reasoning, for example, for encoding execution levels of an access, individual page writes, etc. modeling in IO and normal MMUs turns out to be a challenge because they blow up your state space, and we're mostly using set solvers. So that's an interesting problem that we're solving currently. And then finally, actual trust enforcement through SMMU and IMMU configurations, essentially enforcing the policy that we can come up with on the actual system. And so to summarize, we have seen that SEL4 hardware assumptions don't really match reality. Modern SOCs are distributed systems of untrustworthy firmware. We are, at the systems group, formalizing hardware to derive an explicit formal software trust relationship graph on the entire SOC. And we run SEL4 as a secure CPU driver now with assumptions about the rest of the SOC that's derived from what it actually looks like as far as we know. And I'm very happy to take questions.
Thank you, Roman.
It's me again. Thanks for the talk. This is awesome. Like, this work is so cool. Like, and we absolutely need it. So please, like, just keep doing as much as you possibly can. This is really nice. You were saying you were using a SAT solver on the back end, and that you were hitting some like state explosion problems. As far as I can tell, like, you're just manipulating addresses, and if you're not multiplying two variables together, and you're just doing variable multiplication by constants, you should be able to get a nice speed up by using SMT solvers and like integer theories. Yeah. Have you looked at that, or it doesn't work?
I think we're currently working on it. The primary reason that we have a state explosion is that when you introduce an MMU, the MMU can either you assume that it can remap arbitrary pages to arbitrary other pages, at which point you get like a combinatorial amount of possibilities, or you restrict it so much that it stops looking like an MMU essentially. And we're currently working with specific configurations to work around this issue, but there might be other things that you can do.
Could you briefly explain what you mean by a CPU driver and how that relates to SEL4? Why is there a match there?
Right, the idea is that we're abusing SEL4 for its proofs, and we're only interested in it to drive the CPU underneath, and we don't care that much about the fact that it's SEL4 in particular doing it.
All right, great talk, thanks. How should I say? I'm a little bit, I want to contradict the SEL4 hardware assumptions don't match reality, because when I wrote that sentence, right, you only talk about the first part, that, you know, there's no DMA. Of course, then it's easy. And the second part is I wrote because I wanted someone to do exactly your research, so thanks. But I mean, that's exactly it, right? So the assumption of SEL4 is that you know what the hardware is, what DMA is going to do. You either control those drivers or you control an IOMMU, and if you have like random M0 cores in there, you know how to turn them off or you know what runs on them. That's what that assumption is trying to say. So we're, of course, extremely aware that, you know, this is not what, you know, PDP-11 is not how the world looks anymore. But, yeah, it took a few years, but I'm glad that somebody is working on this.
Any other questions? I have a quick one. If we're formalizing the hardware, then we know about these secret M0 cores hiding. What's stopping us from putting SEL4 there, or some other trusted firmware?
Like in principle, nothing. Some of these cores might be too restricted to run SEL4. Like they might not have enough RAM or enough cache, or like you might run into weird limitations like that. In principle, you could, but in principle, if the core is powerful enough, you could run SEL4 there. It might lead to performance degradation in some cases because these firmware drivers, this firmware might just be like bit banging them. What?
The manufacturer will ship pre-installed firmware in these things. And it was software written by hardware engineers. That's, yeah. There's nothing you can do about it, I'm afraid.
One thing we have thought about is that if you can get SEL4 to run on like a small M0 core like this, you might be able to get SEL4 to virtualize the core underneath and run the firmware on top of SEL4 with an entirely virtualized environment, but that sounds like a lot of work.
Yeah, I was saying you don't have an MMU on M0 core, so you cannot run SEL4 there. That's it.
Yeah, you have an IO MMU.
But SEL4 needs an MMU.
Yeah.
So you cannot really run SEL4 on M0.
Yeah.
Let's thank our speaker again.